In this question, a scientist measures how Seaborgium-265 decays over time and plots the graph of mass against time provided. So we can see we've got mass of Seaborgium-265 remaining on our y-axis and time in seconds on our x-axis. Our first question is, what is the half-life of Seaborgium-265? The half-life is the time taken for half of the original sample to decay. So in this question, we started at 0 seconds with this much, and we can see over time it's decreasing. So we started with 120 grams. So the half-life is the time that it takes for that mass to halve. So 120 divided by 2 is 60 grams. So we know after a half-life has passed, we'll have 60 grams left. So we can look on our graph and see what time the mass has decreased to 60 grams. In this case, it's 8 seconds. So over a time of 8 seconds, the mass halved from 120 to 60. So it sounds like 8's going to be our answer. We could check again though, because half-life doesn't matter where you start. So we could start at 60 instead and say the time to halve from 60, that would be going down to 30 grams, which would be about here on our graph. So if we go across on our graph and see at what time we hit 30 grams, it's at 16 seconds. So going from 60 grams at 8 seconds to 30 grams at 16 seconds, again, that took from 8 to 16, which is 8 seconds. So again, the time to halve the mass was 8 seconds. So 8 seconds is our half-life. And as I've shown, you can measure that anywhere on your graph. It doesn't have to be from the starting mass, but that's often the easiest way to do it. So our half-life we're going to fill in here is 8 seconds. Our next question is to figure out how long it will take for the mass of Seaborgium-265 to drop to 3.75 grams. So we know we're starting with 120 grams. Eventually, it's going to halve and halve again and halve again until we have 3.75 grams. So our goal is to figure out how many half-lives will pass and how much time will pass. So to do this, we're going to track the halving of our mass and see how many half-lives it takes. So we're starting with 120 grams. Over one half-life, that is going to drop to 60 grams. So that is our first half-life. As we saw on our graph here, to drop from 120 to 60 grams took 8 seconds, which is our half-life. Then it's going to halve again. From 60 grams, it's going to halve to 30 grams. So I'm just dividing by 2 each time. So that's our second half-life. Again, we showed that on the graph. Then it's going to halve again from 30 grams divided by 2. That's 15 grams. That's our third half-life. Then it's going to halve again. 15 halves to get 7.5. So we're going to have 7.5 grams after our fourth half-life. 7.5 divided by 2 gets us 3.75. That's after our fifth half-life. So we need to halve 125 times to get to 3.75 grams, which is our goal. So we know it takes 5 half-lives in order for us to get to 3.75 grams. So I'm going to go ahead and fill that in our answer box here. 5 half-lives. Then it asks us how much time will pass. Well, we know each half-life is 8 seconds and we've got 5 half-lives. So our total time is going to be 5 times 8, which is a total time of 40 seconds. So we can go ahead and fill that in our answer box here. Let's do another question. This question is about carbon dating, we're told that carbon-14 has a half-life of 5,730 years, and it's a thing that makes plants such as trees slightly radioactive. A scientist measures the radioactivity of a freshly harvested piece of wood as 918 becquerels per gram. An archaeologist finds a wooden bowl and measures the radioactivity as 115 becquerels per gram. So while the plant is alive, it's constantly taking in carbon dioxide and it's maintaining a radioactivity of around 918 becquerels per gram. But once it dies or is harvested and is used to form bowls and spoons and other things, it's no longer taking in carbon dioxide, so it's not maintaining that radioactivity, and it's going to decay over time based on the half-life. So our goal is to figure out how many half-lives have passed since that wooden bowl was a tree. So we know a freshly harvested piece of wood has a radioactivity of 918 becquerels per gram. After one half-life has passed, the radioactivity is going to halve. So it was 918. 918 divided by 2 is 459 becquerels per gram. So after one half-life, it's 459. After another half-life, it's going to half again. So half of 459 gives us about 230 becquerels per gram. That's our second half-life that's passed. If we halve again, we're going to end up with 115 becquerels per gram. And that's what we were told in the question is the radioactivity of our wooden bowl. So we know that since the wood was freshly harvested, 3 half-lives have passed in order for it to end up with a radioactivity of 115 becquerels per gram. So we can fill that in here. 3 half-lives have passed. Next, to answer how old is the bowl, we're going to take the number of half-lives and multiply it by the half-life of carbon-14, which is 5,730. So we've got 3 half-lives multiplied by 5,730, which gets us an age of 17,190 years. So we can go ahead and fill that in our answer box here. Lastly, we're told the archaeologists found the bowl in 2020 CE, and our goal is to figure out what year was the bowl made. So to figure that out, we're going to take the year it was found, which is 2020, and we're going to subtract the age that it is, which is 17,190. Which gets us negative 15,170. Which means that it was made in the year 15,170 BCE. So we can go ahead and fill that in. So what era is the bowl from? So we can look at our chart here and we can see the names of different eras with different time spans. Now looking at the bottom, from 53,000 BCE to 10,300 BCE, that's the Paleolithic era. And since our bowl was made in 15 something BCE, it's going to fall within that range. So we know our bowl was made in the Paleolithic era. Let's do one last question. In this question, we're told uranium-238 has a half-life of 4.5 billion years, and it's one of the isotopes that makes rocks slightly radioactive. We're told an astronaut finds a piece of rock in space, and it contains 1.56% of the uranium-238 that a newly formed rock would contain. Our goal is to figure out how old is the rock. So initially, a newly formed rock has 100% of the expected uranium-238. After one half-life, it's going to have half of that, which would be 50%. After another half-life, it would have half of 50, which is 25%. After another half-life, it would have half of 25, which is 12.5%. That would be 3 half-lives in. We need to get all the way to 1.56%. So if we divide 12.5 by 2 again, that gets us 6.25%. That's our 4th half-life. If we divide that by 2 again, that gets us about 3.13%. That's our 5th half-life. And if we divide one more time in half, that gets us about 1.56%. That is our 6th half-life. So we can see it takes 6 halvings to get from 100% to 1.56%, which means 6 half-lives have passed. So how old is the rock? Well, we know that 6 half-lives have passed, and the half-life is 4.5 billion years. So that gets us an age of 27 billion years. So we can go ahead and fill that in the answer box here. 27 billion years. So to summarize with half-life, you need to take the initial mass or percent or whatever it may be, activity of your sample, and you're going to halve it repeatedly until you get to the new number you're looking for. The number of times you halve it is the number of half-lives that have passed. To find the total time passed, you can multiply the number of half-lives by the half-life itself.